Hey everybody, welcome to this month's astronomy lesson. My name is Dr. Valerie Rapson and I am the director and astronomer at the Dudley Observatory in Albany, New York. And I'm really bummed that we're not able to get together in person this month to do our astronomy lesson, but I figured the next best thing would be to record a video lesson to share with all of you. So that's what we're going to do today. We're going to do our normal lesson, Wonders of the Spring Night Sky, this month. And we're just going to do it in recorded form here. So the way this is going to work is I'm going to go through my presentation and I'm creating a voiceover of the slides. So you'll hear me describing and chatting just as if we were in person. After we finish with this first slide here, I am going to get rid of the video. Right now you can see me in the bottom screen, but we'll get rid of that moving forward so that you'll just see the slides there. That'll help us save on some data, and when my cats jump in front of the computer periodically, as they like to do when I'm working from home, we won't have to pause and take them down or anything like that. So there's some logistical things. Throughout the presentation, you'll hear my voice. You might also see a red dot moving around the screen. You can see it cutting across the slide there. That is my laser pointer. So if you see the red dot moving around, I'll try and trace out some constellations we're going to talk about or point to things in the presentation. And our goal for today is to talk all about the different constellations in the spring night sky. So we'll cover some of the easiest to find constellations, and we'll also talk a little bit about some of the science behind the stars and other objects that you can view in the spring night sky. Now, the goal is to talk about things that you can easily view outside with your eyes. Almost everything I talk about today, you can just go outside, look up, and find it. Might take a little bit of practice to do that, but they are pretty much all visible with just your eyes. And if you have a telescope or a pair of binoculars, bring that outside with you. As the weather gets warmer here, it'll be easier to stay outside for a little longer, and you can try and find some of these interesting things in the sky. So let's get started with our official presentation here, Wonders of the Spring Night Sky. We'll begin our presentation the same way we begin all of our tours of the night sky, by briefly talking about why we have seasonal constellations in the first place. Why do the stars and objects that I see in the night sky change throughout the year? Well, if you look at my diagram on the right-hand side, it's showing our sun in the middle of the solar system, planet Earth orbiting around the sun counterclockwise, and a selection of constellations or stars beyond the edges of our solar system are shown around the outside here. You might recognize these as the zodiac constellations. It's not all the stars in the constellations we can see in the sky, just an example subset here. So why do we see different patterns, different stars in the sky throughout the year? Well, as the Earth goes around the sun, the direction of nighttime for those of us on Earth changes. If you joined us for our winter night sky tour, in the diagram, Earth was down here around the January time frame. And if we draw an arrow pointing away from the sun, that's towards the bottom of the screen here, the stars that are visible at the bottom of the screen, they would have been up in a January night sky because that's the direction of evening at that time of year. As time progresses forward, as we move from January to April or May into our springtime here, Earth is over on the right-hand side of the diagram. And if we draw a line again away from the sun, the stars on the right-hand side of the picture, now circled in that yellow oval, those are the stars that are going to be visible in the late winter, early springtime sky. And as the Earth goes around the sun, the stars that are visible in the evening sky change. This is what we call our seasonal constellations. And by seasonal, we're talking about the stars and constellations that are visible in that season in the early evening. If you stay up late, the stars will change and you actually get a preview of the next season. So everything we talk about tonight or today are stars that are going to be visible in the evening sky, at least until midnight or 2 in the morning. The early morning sky would be a little bit different, and you'll have to wait and see the presentation for the next season to understand all of those objects. Let's begin with the first and most famous constellation of the springtime sky, Leo the Lion. Leo is going to be in the southeast or the southern sky, depending on exactly what time in spring you go and look for him. And you can see a tracing of the outline of stars that we often imagine playing connect the dots with to make the pattern of the lion. There are two shapes you can look for, a backwards question mark. I'll trace it out here for you. So draw a question mark by connecting the dots in the sky, but draw it backwards from a standard question mark. And then behind that backwards question mark is a small triangle. And what people usually imagine is the question mark is the head and the front paws of the lion, and the triangle represents the tail and the back legs or the hindquarters of the lion. Now there's some pretty interesting stars and objects in Leo, which we'll talk about in more detail. There's a star called Algeba. It's this star right here. And then Regulus is the brightest of all of the stars in Leo, and that one's probably the easiest one to find. It'll be the dot at the bottom of your question mark. There are also some other objects. They're labeled M with a number over here. We're not going to talk too much about these objects in Leo, but we will talk about some M objects in other constellations later on. These stand for Messier objects. They're in this Messier catalog. And like I said, we'll learn a little bit more about them later on in the presentation. To show you quickly what the stars actually look like, here's a nice photo of the real night sky showing you the pattern for Leo the Lion. And if you look closely, you should be able to connect some of the brightest stars to make those two patterns we talked about. Here's our backwards question mark. And then behind it is that small triangle. And you'll have to stretch your imagination to, fill in a whole lion there if you choose to. So let's talk about those two stars I just mentioned, Regulus and Algeba. We'll start with Regulus. The term Regulus means little king or prince. And the star itself should appear nice bright blue in the sky because the star is a blue subgiant. The star is a little bit more massive and a little bit larger than our sun is, and it's evolved to a point where it's actually starting to puff up, become larger, and brighter or more luminous than it was throughout most of its lifetime. You can see a cartoon drawing over here. This is not an actual picture of Regulus. They're actually using a blue image of the sun to represent Regulus here. But it shows you three objects to compare their size. So here's Jupiter to scale. Here's our sun to scale. And then this is how large Regulus would be on that same scale. So you can see that it's a little bit bigger and it's quite a bit brighter than our sun currently is. Now, Regulus doesn't look like anything fancy in the sky. It looks like a bright blue dot, but it's actually part of a quadruple star system. When you use large telescopes, you can actually zoom in close and you realize that Regulus is not just one star, it's actually four stars together. A subgiant, two small stars, so stars that are about the size of our sun or smaller, and then a white dwarf, which is the core of a dead star. So all of these stars are actually together in the sky. They appear as if they're gravitationally bound, orbiting around one another in some way. And it's really an interesting selection because you've got your white dwarf star, which is already dead, Regulus, the actual star, the main star, the blue subgiant. So that is an evolved star that's actually on its way to the end of its life. And then there are two smaller stars that are kind of more middle-aged. They're going through their fusion processes just like our sun is, and eventually they will evolve and turn into subgiants, but they're not quite there yet. So it's really interesting that you see all of these together if you actually point a telescope at Regulus. But with just your eyes, you're only going to see the one bright blue star, the one that actually dominates the brightness of all of these stars in the system. So something really interesting about Regulus is it happens to fall in a very unique location in the sky. It falls right on this line we call the ecliptic. Take a look at the cartoon on the right-hand side. You can see the outline of the pattern Leo the lion. Regulus is the star at the bottom of our question mark. And there's this red line cutting across the diagram labeled the ecliptic. The ecliptic is the apparent path that the sun takes against the background stars as the position of the sun changes throughout the year. So because the Earth goes around the sun, if we were to look up at the sun in the daytime sky, it technically sits in front of some stars that are up there in the sky. We don't see the stars because the sun outshines them, but if we had the ability to block out the sun, we could see a constellation in the sky during the day, and the sun would fall in one of many different constellations at different times of year. As the Earth goes around the sun, the location of the constellation the sun is in changes throughout the year. The path that the sun follows across the sky through the constellations, that is what we call the ecliptic. Now, because the entire solar system, all of the planets, including the Earth, sit in a roughly flat plane as they orbit around the sun, when we see planets in our day or evening sky, they also follow this ecliptic. Now, the planets, they might fall slightly above or slightly below the ecliptic, but in general, they're going to follow that red line. They're going to follow the ecliptic. And because the ecliptic crosses pretty much right over Regulus, every once in a while, some of our planets are actually going to cross in front of or occult the star Regulus. They're going to block out the light from Regulus. Now, this is something fun that amateur astronomers love to go outside and watch, but it also offers scientists some unique opportunities to make some measurements. If we have a planet that's crossing in front of Regulus, we can actually watch it move in front of the star and use its motion and the time it takes to move in front of the star to get a sense of how large the planet is. And that's actually how we have measured the diameter of many of our gas giant planets out at the edges of the solar system. We've watched them occult stars and we can get a sense of how wide they are. Now, if a planet has rings, as all of our gas giant planets do, we can even detect rings around a planet. And I'll show you a quick diagram that shows how we do that. Here in the cartoon, we have a distant star. You might imagine that being Regulus. And in this cartoon, we're showing Uranus as an example. Here's Uranus, and Uranus is moving from top to bottom. And our perspective as the observer is over on the right-hand side. So imagine looking through a telescope at the star, not the planet, at the star, and having Uranus cross in front of your field of view. As the planet crosses in front of the star, the planet's going to block all of the starlight. And as any rings cross in front of it, and you can see them blown up here, there's kind of 3 distinct sets of rings around Uranus, the rings will actually block out some of the star's light as well. And that's what's shown on the graph in the bottom here. Here you've got time moving forward, so this is time that we're watching Uranus move downward and the rings cross in front of the star. And this axis is intensity of starlight. So as time goes by, Uranus crosses in front of the star. The star is normal brightness when there's nothing blocking it. But as the rings go in front of the star, you can see that we lose some starlight. So 3 rings, we see 3 major drops in brightness. And the squiggles give us a sense of density, how thick the rings are. That governs their ability to block that distant starlight. So just kind of neat that the stars, especially the bright ones that happen to fall on the ecliptic, allow us to do some neat measurements with planets in our solar system without us actually having to go to the planets and make these types of direct measurements. And we do use Regulus whenever it gets occulted to make these kind of measurements. The other star I mentioned in Leo is called Algeba. That term actually translates to forehead, which is kind of weird because it's never really drawn as the forehead of the lion. So I put a cartoon of Leo here. It's got some of the stars labeled. Regulus is usually depicted down at the bottom here as part of the legs, and Algeba is almost always like the back of the neck or the back of the mane. So I don't know, it must have been a different culture than the Greeks and Romans that named this originally. But the name doesn't matter. That's not the point here. The point here is there's something really cool happening with Algeba. Algeba, first of all, is not just one star. It's another binary pair. It's actually two stars, two giant stars that were at one point similar in size to our sun and now have evolved towards the end of their lives. They've puffed up to become these giant stars. And you can see them through a telescope here. If you actually zoom in on those two stars with a small telescope, you'll notice that there's two individual bright dots, not just one. This will be a recurring theme, by the way. Just by chance, a lot of the stars that we're going to talk about today in these constellations all happen to be in multiple star systems. Now, the stars themselves, they are individually separated by 170 astronomical units or 170 Earth-Sun distances. That's about twice the diameter of our solar system. So go to the sun, go all the way out to Pluto. That's a radius, half the diameter. The entire width of the orbit of Pluto is about 80 AU across. That's the whole diameter of our solar system. So these stars are separated by about 2 solar system widths. And there are some exoplanets, planets that orbit around other stars in the sky. And one of those stars actually has possibly 2 exoplanets around it. One of them has been detected for sure. There's an exoplanet 9 times the mass of Jupiter. So it's a very large gas giant planet. There's a cartoon depicting it here at the bottom of the slide. And that planet orbits just one of the stars. It doesn't go around both of them, but it orbits one of the stars in 429 days. So it's at a position just slightly further away from the star than Earth is from our sun. There's also some data that suggests that there might be a possible second gas giant planet orbiting quite a bit further away. So if there's a second planet there, it would be orbiting in like 1340 days. So it would be much further out than the first exoplanet is. But kind of neat to be able to just go outside, look for a bright star, and know that there's at least one planet orbiting around it. And this one is particularly unique because both of these stars appear to be giants. They appear to be more evolved. And as our sun evolves 5 billion years from now, it will become a giant too. And it's unclear what's going to happen to the planets in our solar system at that time. But this is inspiring because clearly some planets are surviving their stars evolving to become giants. So maybe the planets in our solar system will survive as well. All right, let's move on to the next constellation, Cancer the Crab. Cancer is a constellation that sits to the right or in front of Leo the Lion. Remember, if you can find that backwards question mark in the sky for Leo, you can look right to the right of it, and you can look for some stars that are fairly faint, but they'll make an upside down letter Y. That's representing the crab in the sky. Now, these stars will be quite a bit fainter than the ones in Leo, so if you live in the suburbs or near a city, it might be a little bit tricky to actually spot these stars. But if you can, look for that upside down letter Y. And not every constellation really has a connect the dots pattern that actually represents what the name is describing. So I'll just put up here, how people often imagine Cancer. The letter Y usually kind of fills a sideways picture of a crab here. But again, it's totally up to you to use your imagination if you really want to imagine the picture. But I'll be kind of showing you some connect the dots patterns that you can use to find where the constellation is in the sky, because the stars are what you actually see. The crab figurine, you've got to dream that one up all on your own. Now, the constellation of Cancer, while the stars are faint, there's some pretty interesting things embedded in this part of the sky. The main one here, or the first one that we're going to talk about, I should say, is this thing here, the Beehive cluster. So let me show you what that is. And then we're going to talk about another star that's actually off to the left a little bit in Cancer that has a really interesting planet orbiting around it. So we'll start with our Beehive cluster here. This is M44 or Messier 44, those objects in the Messier catalog I mentioned. The reason it's called the Beehive cluster is because when early astronomers looked at it through a telescope for the first time, they thought the stars looked like a swarm of bees, so they nicknamed it the Beehive cluster. If you look at it through a telescope, you will see something like the picture depicts on the bottom here. What you're looking at is an open cluster of stars. That is a collection of bright stars that are all physically gravitationally bound together in outer space. Now, the cluster in this picture is all of the bright blue dots that you see. So there's quite a few blue dots near this concentration in the center. There's some blue dots towards the edges as well, scattered about. Most of the fainter white dots that you see around the edges here, those are stars that are much further away in the background. So the main stars, there's about 100 of them that are technically part of the cluster. They're all the same distance away from us and they're all gravitationally bound together. Those are the bluer dots that you see in this image. The cluster itself is about 600 light years away, 23 light years wide, and it's a great example of something that often happens with star clusters. We call it mass segregation. What's happening is you have a couple of massive stars that are born in the cluster, and because they're more massive, they have a stronger gravitational pull. Stars that form nearby, they're going to be gravitationally pulled closer to those massive stars. That will become the center of the cluster, and their collective gravity will work to pull in other material. And what ends up happening is the most massive stars that form in this region of sky, they're all going to settle down towards the center. And that's exactly what you see. Most of the stars that are the brightest, the most massive stars, they are near the center, collected together. And there are some brighter stars out at the edges as well, but they're not quite as bright as most of the stars in the center. That means the stars at the edges are a little bit less massive, they're not quite as big and bright. All of those more massive stars have settled towards the center. We see this, as I said, often with star clusters in the sky, where the most massive stars kind of pull in the material, making a dense cluster in the center and a less dense scattering of stars further out to the edges of the cluster. So that was the Beehive. Now I want to show you this really interesting star-planet system. There's a star called 55 Cancri, and it's very, very faint. It's honestly not something that you're easily going to spot with just your eyes unless you're in a really dark sky. But if here's the upside down Y, the Beehive cluster is right above the word Cancer here. 55 Cancri is a faint star just to the left of the star that's the top of the bottom of the Y. Now, this star is, again, a binary star system, two stars that are gravitationally bound together, orbiting around one another, and they are roughly the size of our sun. But what's interesting is that I said there are planets orbiting around this star. In total, there are 5 exoplanets that orbit the slightly larger of the two stars in the binary system. So the planets are not going around both stars, they're only going around one of the two stars. An analysis of these exoplanets tells us that there are 4 gas giant planets and 1 rocky planet. So most of them are big puffy planets like Jupiter or Saturn. There's only one of them that's smaller and rocky like Earth. Now the whole system is quite compact. Most of the planets are very, very close to the star, and I can show you how their orbits compare to planets in our own solar system. The white box here is showing our sun, and there are blue lines that represent the orbits of Mercury, Venus, and then the Earth. On top of this image is showing you where the 5 planets in 55 Cancri would be located if they were in our solar system, which they're not. They're around a completely different star. But if they were in our solar system, where would they be? Well, 55 Cancri E, B, C, they are all within the orbit of Mercury. So all three planets would be closer to the sun than Mercury is to our sun. 55 Cancri F is about at the orbit of Venus. You can see it doesn't quite match the orbit of Venus. It goes a little further out, but roughly at the location of Venus. And then there's one planet missing from the diagram. That planet is one of the gas giant planets, and it actually sits in an orbit that's very similar to Jupiter's orbit in our own solar system. Now, I mentioned 4 of these are gas giants. One of these are rocky. And that one rocky planet, that's 55 Cancri E, the planet that is closest to the stars there, that is the one that is particularly odd and exciting. So let me tell you just a little bit more about that exoplanet. Here's a cartoon showing 55 Cancri E. You can see there's a star here, and the rocky planet is represented right next to it. And it looks like it's drawn kind of hot and molten in the picture. That's because the planet is so close to the star, it must be incredibly hot. Now, the planet, while it's still a rocky planet, is a little bit larger than the Earth, about 8 times the mass, 2 times the diameter of the Earth. And because it's so close to its star, it orbits very, very quickly. It only takes 18 hours for this planet to go around the star once. So 1 year for this planet is only 18 hours. It goes around incredibly fast. Now, because of its close proximity to the star, it is indeed very hot. Temperatures probably range on that planet from 2,500 to 4,000 degrees Fahrenheit all the time. So very, very hot planet, not somewhere that I would want to go to live. Now, that's not the only interesting part about this planet. Astronomers were exploring this system, and they started to take a closer look at the star that the planet orbits. They used spectroscopy and other techniques to get a sense of the materials that make up the star. And what they found is that while the star was composed primarily of hydrogen and helium, like most stars, it had a particularly high amount of carbon as compared to what we would expect for a star of its size. Turns out it had fairly high levels of carbon and fairly low levels of oxygen. Now, why is this at all interesting and relevant? Well, the amount of material that's not hydrogen and helium inside of a star gives us clues to what the nebula was like that originally formed the star and the planetary system. So if this star is enriched in carbon, then the planets that are orbiting around the star likely have higher amounts of carbon as well. So what does that mean for 55 Cancri E? Well, if this planet is really, really dense, if it has a high amount of carbon, then we can do some modeling to show what the interior of the planet might look like. And at very high temperatures and a very dense center, you would have carbon that is highly compressed. And some of the models actually show that the interior of the planet could be filled with diamonds. Yes, diamonds, like the diamonds that we have in our rings and our jewelry, that kind of diamonds. So there was a huge news article not too long ago with pictures like the one in the upper right there. That is a cartoon, that is not a real image. But you know, they were talking about the diamond planet, right? You could theoretically dig through the crust of this planet and just reach a purely diamond interior. Now, unfortunately, after more modeling and studying, most astronomers don't actually believe that this is true. There probably is elevated levels of carbon in this planet, but it's not necessarily solid diamond on the interior. We really need to gather more information about the star and the planet itself before we can make quite as bold of a claim as they did in some previous articles. But interesting that this planet has such a dense interior and so much carbon that it actually could literally be filled with diamonds on the inside. So I haven't given up hope for it yet, but it goes to show that, not all these planets that we're finding around other stars in the sky are going to be anything like what we have here on Earth. In some cases, they're going to be extremely different and extremely unique, like this one. All right, let's move on to our next constellation, Virgo the Virgin. In most Greek and Roman mythology, she is called the Virgin, although in some of the stories she often personifies the Greek goddess of Persephone, and Persephone is the harvester. So sometimes you will see her referred to the Virgin, and sometimes you'll see her as the harvester. Having that harvester story is really great for somebody like me who has to teach in a planetarium to middle school students. And you might imagine that being able to point her out as the harvester as opposed to the virgin helps me avoid a lot of difficult questions that I don't want to get into in an astronomy class. So either one works. Now to find Virgo in the sky, there is a patch of fairly faint stars along with one bright star called Spica. You can connect the dots to try and imagine like the body, the legs, and then maybe the arms of a lady. But again, you can imagine however you want to in the sky. The main star that you do want to look for, though, is that star called Spica. Spica is a bright blue star in our sky, and it'll look something like the picture in the upper right-hand corner. That's a picture with a telescope, so it's zoomed in a bit and a little brighter, but it will be distinctly blue color in the sky. Going along with our theme so far, Spica is indeed a binary star system, two stars orbiting around one another. Both of the stars are a bit more massive than our sun. One is 7.8 and the other is 4 times the mass of our sun. And that system is 260 light years away from us. Now, the two individual stars, you're not going to be able to see them distinctly with your eyes, and even with the best telescopes, you really can't distinguish between the two stars. They are separated by only 11 million miles, and to help give you a sense of scale, Mercury sits about 40 million miles from our sun. So if these two stars were together in our solar system, if one was at the position of the sun, the other would still be very far into the orbit of Mercury, be much closer to the sun than Mercury is. Now, because these stars are so close, they actually have a gravitational influence on one another as they orbit. This is a cartoon, but it shows what the stars might look like if we could actually resolve both of them. Notice that the two stars are not perfectly round. They're actually squished a little bit into ovals. And that's because the gravitational pull from one star onto the other, it's actually going to tug on the star at the star's equator and cause them to flatten at the poles and be wider at the midsection. So these two stars are actually a little bit more oval shaped. And you can even see that there's like some material around the outside of the stars in this cartoon. It's possible that the gravitational pulls combined with any stellar winds that they have actually cause them to exchange a little bit of material. But to our eyes, Spica is just going to look like a standard blue star in the sky. And it's the main one you want to look for kind of in the east and southeastern sky in early spring to find the constellation of Virgo. There's a constellation that sits right above Virgo in our sky. It's called Boötes, and Boötes is usually defined as the herdsman. We usually depict him, as you can see in the cartoon on the left, with two dogs, hunting dogs or herding dogs. And it doesn't really show well in this picture because I've kind of blocked it here, but Ursa Major, the great bear in the sky, is here. So the stories often imagine him with the hunting dogs or the herding dogs kind of chasing the bear around the sky. Boötes is another constellation that's a little bit tricky to find because the stars are fairly faint. But there is again one bright star that you can look for. This one is going to be a little bit more red in color, and it's called Arcturus. So looking at the pattern of stars over here, there's Arcturus. And then there's kind of a connect the dots shape up here that represents the body of the person, and then kind of two legs over here to the left and the right coming off of Arcturus. Arcturus will sit not too far above Virgo and above Spica. So in the sky, you can actually find Arcturus, and then you can move down the sky to find Spica, noting that Spica will be blue or white, and Arcturus will be kind of distinctly orange. That's how you can tell the difference between the two. Arcturus is a red giant star, so it's an evolved star, puffed up. That's why it's nice and bright, and it turns kind of red in color because it's a little bit colder than it used to be. And it sits about 36.5 light years away from Earth. Now within this constellation, there's a really interesting object, M3. It sits just to the right of the stars that we usually play connect the dots with. Let me show you M3 up close. So M3, or Messier 3, is a globular cluster of stars. Recall that we saw the Beehive cluster already. That was an open cluster. This is a globular cluster, literally a glob of stars in the sky. The cluster, you can see a picture of it here through a telescope. It's composed of over 500,000 stars, all of different sizes and colors. Notice that it seems to be fairly densely packed in the center, with a little bit more dispersed stars at the edges. And some are blue, some are white, some are red. That gives you a sense of their evolutionary state, their sizes, as well as their temperatures. The cluster overall is fairly old. It's 11.4 billion years old, sits about 34,000 light years away from us, and is about 90 light years in diameter. So from side to side, the whole cluster goes about 90 light years. This globular cluster is interesting because it's actually the first object in the Messier catalog that was discovered by the guy who we named the catalog after, Charles Messier. He was putting together this catalog in the late 1700s. He saw this one in 1764. And just to give you a little background on the Messier catalog, Charles Messier was looking through a telescope at stars and objects in the sky, and he was actually searching for comets. And as he was looking through the telescope, he found a whole bunch of objects, 110 of them to be exact, that didn't look like comets and definitely weren't just a single star. So this list is basically the brightest objects in the night sky that aren't stars and aren't planets. And like I mentioned, in the current catalog, there's about 110 of these objects, and M3, or Messier 3, was one of them. So this is a beautiful globular cluster. You can try and spot it. Great to look at with a pair of binoculars in that constellation of Boötes. Moving on to our next constellation here, Libra the Scales. Libra, again, is a fairly faint pattern of stars in the sky, but it has two of the most interesting star names that I have ever seen, and I'm going to do the best I can to pronounce them. These two stars in the sky here, the top one is called Zubin Shamali, and the bottom one is called Zubin el-Janubi. And I'm pretty sure I said that right. I practiced this a lot before I recorded the presentation. But these names, they sound really funny. What they mean, Zubin Shamali means the northern claw, and Zubin el-Janubi actually means the southern claw. Now, why are we talking about claws when we're representing Libra the scales? Well, this actually goes back to the ancient Babylonians who provided some of the names for these stars, and they actually imagined that what we now call Libra was an extension of Scorpio, the scorpion, which is in this region of sky too. You can see that Scorpius is labeled down over here. So these couple of stars often represent the head of the scorpion, Antares is the heart of the scorpion, and the Babylonians imagined the claws of the scorpion going all the way up to these two stars here. So they named them the North Claw and the South Claw. Nowadays, we've adjusted things. The Greeks and Romans did it a little differently, so we added Libra the scales in here and kind of condensed the constellation of Scorpius. Now, along with those two really cool stars, also in this part of the sky is this interesting object, HG 140283. Now, I'm cheating a little bit because this star is actually part of Ophiuchus, a different constellation that we'll talk more about when we do our summer nighttime sky presentation. But it's so close to Libra and so interesting that I have to spend a few moments talking about it. So HD 140283 has a cool nickname. It's called the Methuselah star. Now, Methuselah, she was a patriarch in the Bible, and she lived to be 969 years old, the oldest figure or longest living figure in the Bible. So, with that nickname, you might be thinking, well, the star better be pretty old, right? That's probably why we call it the Methuselah star. And indeed, you would be correct. So, this object, this star, is the oldest known star in the universe. 14.27 billion years old, plus or minus 800 million years. There's some pretty distinct error bars on this, which I know 800 million years sounds like forever, but in astronomy, that's actually not too bad. Usually we don't know the ages of stars to quite that accuracy. But if you've been following along with past presentations, you might remember that we've talked about our universe, and the whole age of the universe is only believed to be 13.8 billion years old. So that would mean that this star is actually older than the entire universe. Now, of course, that can't be correct. We don't think this is a visitor from another universe or anything like that. If you look at the error bars, if we actually did minus 800 million years on this, we would be within the range of the age of the universe. But regardless, this is still a very old star. And it's possible that we are slightly off in our measurement of the age of the star, or slightly off in our measurements of the age of the universe. There's definitely some wiggle room in both of those numbers. But we're pretty confident they used a bunch of different techniques. You can see looking at the brightness, the amount of iron in the star, and using stellar models. They're pretty confident on their age, plus or minus that 800 million year mark. So the star is definitely really old. It likely formed at the very beginning of the universe. And the star right now is within the Milky Way galaxy. It's 190 light years away. And it's moving through the galaxy at very high speeds. It's moving through at about 800,000 miles per hour. Now, normally stars don't do that. Normally stars don't move quite that fast. So because this star is so old and because it's moving so quickly, we actually think that this star is not part of the Milky Way galaxy. And by the way, the Milky Way galaxy, we believe, wasn't formed until about 2 or 3 billion years after the beginning of the universe. So the Milky Way itself is only about 12 billion years old. This star, however, is definitely older than that. And we think it came from a dwarf galaxy, a smaller galaxy that was once orbiting the Milky Way, and the Milky Way cannibalized it. The Milky Way gobbled up this galaxy. Using its gravity, the galaxy and the stars fell into the Milky Way, and there's no longer a galaxy component for us to see of this cannibalized galaxy. But there would still be potentially a couple of stars left over flying through at high speeds, and we think the Methuselah star is one of them. So this is the oldest known star we have ever seen, kind of rivals the current believed age of the universe, and it's really just an intergalactic visitor. It's left over from a galaxy that was eaten by our own Milky Way galaxy long ago. So let's pivot now, literally pivot our bodies and turn away from our southern and eastern sky over to our northern sky. We're going to look for some of the most famous constellations in the nighttime sky. We'll start with the Big Dipper and Ursa Major. Now, the Big Dipper you're probably familiar with. That's the spoon in the sky, the 7 stars that we connect together to make the spoon or the ladle. But the Big Dipper is actually not a constellation all by itself. It's what we call an asterism, which is a group of stars that make a familiar shape in the sky. The constellation is technically that entire region of sky, not just the stars that we play connect the dots with, but all of the stars that are within that patch of sky. The Big Dipper is an easy pattern of stars to find, and it's part of Ursa Major, the Great Bear. We can continue to play our game of connect the dots as you see in the cartoon here, and we can imagine that the Big Dipper is the tail and the body of the bear. Add some stars for the face and the rest of the body, some stars for the front paws, and then stars for the back paws of the bear as well. And just so you can see what it looks like in the real sky, in that photograph you can probably pretty easily pick out the Big Dipper. That's right here. And then you've got the nose and the front of the bear, the front paws, and the back paw of the bear there. So these two things, the Big Dipper, that's the easy pattern to find. That's actually part of Ursa Major, the entire constellation that fills a chunk of our northern sky. Let's look a little bit more closely at the Big Dipper for a moment. The Big Dipper is always located in the northern sky. It might be tilted a different way depending on what season you're looking for it, but you can always find the Big Dipper. If you're here in New York State and in most of the northern hemisphere, you can always spot the Big Dipper. Each of the stars have fun names there, and the one I want to mention real quick is actually, again, double star, Mizar and Alcor. Now, Mizar and Alcor are the two individual binary stars, and they themselves are actually in multiple star systems. So in total, I believe there are 6 stars within the system altogether. But to our eyes, what we can actually spot is 2 individual stars. Now, what's additionally neat about Mizar and Alcor is that they were actually used as an ancient eye exam. People would go outside, they would look for Mizar and Alcor, and see if they were able to distinguish those 2 stars individually in the sky. If you go outside and you can see both Mizar and Alcor, if you can tell that there's 2 stars in the handle of the Big Dipper there, then you have 20/20 vision or better. If you can't tell that those are 2 individual stars, then your vision is unfortunately not 20/20. And before they had, real eye exams and eye charts, they actually used these stars to test and see how good or how bad somebody's vision was. And this is something that you can do today. You can go outside tonight, look for the second star in the handle of the Dipper, see if you can distinguish 2 individual stars. If you do, your vision is great. And if you don't, maybe you need to get a pair of glasses or update your prescription or something like that. So fun challenge. I encourage you to go outside and just see if you can spot Mizar and Alcor and tell if there are actually 2 stars there. The Big Dipper is fun and easy to find, and it's also a great guidepost to one of the most important stars in the sky, the North Star, scientifically named Polaris. Now, to find the North Star, we can use the Big Dipper. Find the handle and the cup of the Big Dipper, then use the 2 stars at the end of the cup, point away from the Big Dipper, and the next bright star that you get to, that will be Polaris. That will be the North Star. Notice the Polaris is also the end of the handle of the Little Dipper. So there are stars, and they're very faint, but there are some stars that actually trace out the handle and the cup of the Little Dipper, and they tip in opposite directions. We often imagine the 2 dippers being able to pour water into each other's cups. Now, in a city sky, the stars in the Little Dipper might be a little too faint for you to see. Usually you can see Polaris and maybe the 2 stars at the end of the cup of the Little Dipper, no matter where you are. But if you're in a darker sky, you will actually be able to trace out an entire shape of a Little Dipper, as well as seeing Polaris and those other brighter stars. Now I have one more cartoon that shows you the same thing, and I wanted to show you what it'll look like now. If you go out early springtime sky, the Big Dipper will be standing up on its handle, and as time goes by, it will actually move upwards in the sky a little bit. But this is kind of what you will see in around April time frame. The handle of the Big Dipper will be here, the cup here. You use the two stars at the end of the cup to guide you across the sky to the North Star. You might see some stars in between, but you want to head towards the brighter star that is in that region of sky. There's also another constellation, which we're not going to talk about thoroughly today, Cassiopeia, our queen. It's a W or an M shape, and the central dot there actually always points out away from the W or the M shape towards the Big Dipper, or excuse me, towards Polaris as well. So you can kind of use the two, the Big Dipper and Cassiopeia, to guide you to the North Star. One big misconception that I want to make sure that I cover is that people think Polaris, the North Star, is the brightest star in the night sky. It's actually not even close. Those of you that saw my wintertime star lecture might remember that we talked about the brightest star in the night sky, and it is called Sirius. Sirius is part of Canis Major, the big dog, and you can see it in the cartoon here. Sirius is in the southern sky in our winter time, and it's a lot brighter than Polaris. Polaris is actually 25 times fainter than the star Sirius, and there are at least 40 other stars in the night sky that are brighter than Polaris. So Polaris is great. It's our North Star. It happens to be lined up exactly with Earth's North Pole. That's why it's special. But it is not the brightest star in the sky. This is a big misconception that has perpetuated generations. And I try and teach every kid that I meet that the North Star is not the brightest. And usually they go home and teach their parents that the North Star is not the brightest star in the sky. So now I'm teaching all of you. Polaris is not the brightest star in the sky. Sirius is the brightest star in the night sky. Now, even though Polaris is not particularly bright, it is still incredibly useful, right? So it's lined up right now almost exactly with Earth's North Pole. So if you can find Polaris, then you know that that direction is north. And if you're in the northern hemisphere, you can actually use the North Star to tell you your latitude here on Earth. So in my cartoon here, you've got a person that is using an astrolabe or some other device to look at the North Star and measure the angle of the North Star, meaning how high above the horizon is the North Star. If you measure it accurately here in Albany, you should get a number that's about 42 or 43 degrees above your horizon. Albany's latitude is 42.6 degrees north. So the height of the North Star, because it's lined up exactly with Earth's North Pole, that will tell you your latitude anywhere in the northern hemisphere. So if you can see the North Star, you can actually determine your latitude. That is how people that sailed used to do it, right? They used to look for the North Star to figure out exactly where they were. There's all sorts of different historical pieces that talk about the significance of the North Star and how people used it to guide them to the right direction. So the North Star, again, is special. It's lined up with Earth's North Pole. You can use it to measure your latitude, but it's not the brightest star in the sky. Sirius is the brightest star in the sky. Don't you forget that. So we're reaching the end of our presentation here. I know I threw a lot of information at you, and these presentations about the night sky can definitely be a little overwhelming, especially without me being able to take you outside to actually show you these things. The best I can do here is to show you an image of what the night sky would look like in the early evening this time of year. And that's what I have here on this slide. This is a really nice screenshot from some planetarium software. The red letter S depicts south, so these stars are directly south. East is to the left, west is to the right. And you can find some of the star patterns that we looked for. We mentioned Leo. Leo will be in the southeastern and progressively more southern sky as the season goes on. If you look for Leo, then you can look for Cancer right in front of it. You can also go behind Leo to get to Virgo. Spica is that bright blue star down in Virgo. Straight above it is Arcturus, part of Boötes. We also talked about the Big Dipper and Ursa Major. That's going to be in the northeastern sky this time of year. And remember I said that you've got to wait a little while for Libra to come up, but Libra, the scales would be down just below the eastern horizon in this picture here. But you can see that if you go out maybe a few hours after the sun sets in the springtime. Notice too that there are still some other constellations visible from the winter. Orion is over here, Gemini, and that bright star Sirius is also still visible. So I encourage you to go outside and challenge yourself. See if you can find any of these star patterns. Look for these spring patterns. Look for the Big Dipper. That's an easy place to start. And if you're familiar with the wintertime sky, look for Orion and Sirius as well. They can help guide you to at least the right direction that you want to go to find your springtime stars. And there are many other constellations that you see here that we didn't have time to talk about today. I really tried to keep this to under an hour here. So you can do some of your own exploration, looking up things online about these constellations and how to find them. Now, if you want to download your own sky map, you can go to a website, skymaps.com. Very easy to find. And that will print you out a really nice circular map that I would have handed out to you in person that has all of these constellations on it and some directions on how to find them and cool things to look for this upcoming spring. So I encourage you to print your own sky maps at skymaps.com. Okay, well, you have reached the end of this presentation. Next month, I'm planning to talk about satellites and space junk. So we're going to talk generically about what satellites are, how many are up there, where they sit in orbit around the Earth. And we're also going to talk about SpaceX's Starlink satellites and why some astronomers are not too thrilled with Elon Musk putting up all of these satellites in orbit around Earth. And you'll learn about why next month. Hopefully we'll be able to meet in person next month. Otherwise, I hope to do another video presentation if that's not possible. If you guys have questions, you can always feel free to reach out to me via email. My email is at the bottom of the slide here, vrapson@dudleyobservatory.org. Hope you all stay well and healthy, and hopefully I will see you all next month.